For most of human history, magnetism looked like a simple and almost mechanical phenomenon. A piece of iron sticks to a magnet. Two magnets attract or repel. Invisible lines of force seem to stretch through space, pulling objects together or pushing them apart. Classical physics tried to explain this using familiar ideas: moving electric charges, tiny circulating currents, or hidden mechanical motions inside matter. These explanations felt comfortable because they fit our everyday intuition, but comfort in this case was misleading. Magnetism is not a classical force in the way gravity or friction appear to be. At its deepest level, magnetism is a quantum effect, rooted entirely in the strange behavior of electrons and the rules they obey. To understand why this is such a radical statement, it helps to think about what classical physics expects. In the classical world, forces come from motion or interaction between objects that can, at least in principle, be visualized. A thrown ball moves because a force acts on it. A current in a wire produces a magnetic field because charges are physically flowing. Early scientists naturally assumed that magnets must work the same way. They imagined tiny loops of electric current inside atoms, endlessly circulating and generating magnetic fields. This picture seems logical, but it collapses under careful examination. If magnetism were purely classical, atoms would behave very differently than they do, and many everyday magnetic phenomena would be impossible. The first crack in the classical picture appears when we ask a simple question: why are most materials not magnetic? Everything around us is made of atoms, and atoms contain electrons. Electrons carry electric charge, and moving charges create magnetic fields. If classical reasoning were correct, nearly all matter should show strong magnetic effects, but it does not. Wood, plastic, glass, water, even most metals show little or no magnetism. This is not a small detail. It is a direct contradiction of classical expectations, and it demands a deeper explanation. Quantum mechanics provides that explanation, and it does so by changing the very nature of what electrons are. In the quantum view, electrons are not tiny charged balls orbiting a nucleus along neat paths. They are described by wave, functions, probability distributions, and quantized states. Most importantly, electrons possess an intrinsic property called spin. This spin is not something classical physics can truly represent. It is not a literal rotation of a tiny sphere. Instead, it is a fundamental quantum feature, as basic as mass or charge. Electron spin turns out to be the true source of magnetism. Each electron behaves like a tiny bar magnet, with a magnetic orientation that arises directly from its spin. This alone shatters the classical idea of magnetism. Nothing is physically spinning in the usual sense. There is no miniature wheel turning inside the electron. The magnetic behavior exists because quantum mechanics says it must. Spin is built into the fabric of reality, not derived from motion. Once spin enters the picture, magnetism stops being a mystery of forces and becomes a story about organization. In most materials, electrons pair up. When two electrons share the same orbital state, quantum rules require their spins to point in opposite directions. This pairing causes their magnetic effects to cancel out. As a result, the material appears non-magnetic. Nothing has gone wrong. Magnetism is still there, but it is perfectly balanced and therefore invisible. This cancellation is not an accident. It is enforced by the Pauli exclusion principle, one of the cornerstones of quantum theory. The exclusion principle states that no two electrons can occupy the same quantum state at the same time. This rule has no classical equivalent. It does not arise from forces or collisions. It is simply a rule about how nature is allowed to exist. And yet, it controls the magnetic properties of matter on a macroscopic scale. In certain materials, however, the balance breaks. In elements like iron, cobalt, and nickel, the quantum structure of atoms allows some electrons to remain unpaired. These unpaired electrons have spins that can align with one another under the right conditions. When many electron spins align in the same direction, their tiny magnetic effects add up instead of canceling out. This collective alignment produces a magnetic field strong enough to be observed, touched, and used. The key point is that this alignment is not caused by a classical force pushing the spins into place. It arises because of quantum interactions that minimize the total energy of the system. Electrons are not choosing alignment out of preference. They are obeying quantum rules that favor certain arrangements over others. Magnetism, in this sense, is an emergent phenomenon. It appears not because it is fundamental on its own, but because quantum mechanics allows large numbers of electrons to behave coherently. This idea of emergence is crucial. A single electron's spin is weak and almost meaningless on its own. But when trillions of electrons act together under quantum constraints, something entirely new appears. A magnet is not just a collection of atoms, it is a large-scale expression of quantum order. The fact that such order can persist at room temperature in solid objects is one of the quiet miracles of physics. Classical physics cannot explain this persistence. According to classical reasoning, thermal motion should quickly disrupt any alignment. Random vibrations should destroy magnetic order almost instantly. Yet magnets remain magnetized for years, decades, sometimes centuries. The reason is that quantum energy barriers protect the aligned state. The system becomes trapped in a stable configuration, not because it is mechanically locked, but because quantum transitions to other states are highly unlikely. Even the magnetic field itself is deeply quantum in nature. While it can be described using classical equations for practical purposes, its origin lies in quantum electrodynamics, the quantum theory of fields and particles. The field is not a static substance filling space. It is a manifestation of underlying quantum interactions, a macroscopic shadow of microscopic rules. This quantum origin explains why magnetism can exist without continuous energy input. A permanent magnet does not need to be powered or maintained. Nothing is flowing, nothing is spinning in the classical sense. The magnet simply occupies a stable quantum state. This idea is profoundly counterintuitive. In everyday life, stability usually requires balance of forces or ongoing motion. In quantum mechanics, stability often comes from allowed states and forbidden transitions. The realization that magnetism is quantum also explains why it can suddenly disappear. When a magnet is heated beyond a certain temperature, known as the Curie temperature, it loses its magnetism. Classical physics would struggle to explain why heat should suddenly destroy a force. Quantum mechanics explains it clearly. Thermal energy disrupts the delicate spin alignment, allowing electrons to occupy different quantum states. Once the collective order is broken, magnetism vanishes not gradually, but as a phase change. What makes this even more unsettling is that magnetism does not belong to individual atoms in isolation. An isolated iron atom does not behave like a tiny fridge magnet. Magnetism arises from interactions between atoms, from shared quantum behavior across a lattice. This means magnetism is not a property of parts, but of relationships. It exists only when quantum systems cooperate. This cooperative behavior challenges the classical idea that understanding something means breaking it into smaller pieces. In magnetism, the whole is genuinely more than the sum of its parts. You cannot fully explain a magnet by studying a single electron. You must understand how quantum rules bind electrons together into a unified state. When viewed this way, magnetism becomes a powerful lesson about reality itself. It shows that the world we experience is not built from solid objects obeying simple forces. It is built from abstract rules, probabilities, and constraints that operate at scales far removed from human intuition. The pull of a magnet on a piece of iron is not a mechanical tug. It is the macroscopic consequence of quantum rules written into the behavior of electrons. This realization truly does shatter everyday understanding. It means that something as ordinary as a magnet is evidence that classical reality is not fundamental. The solid, predictable world is an approximation, a surface appearance. Beneath it lies a quantum domain where properties exist without motion, forces arise without contact, and stability comes from rules rather than mechanisms. In this sense, magnetism is not just a physical phenomenon. It is a message. It tells us that the universe does not work the way our instincts suggest. It works the way quantum mechanics demands. Every magnet quietly proves that reality is stranger, deeper, and far more elegant than classical physics ever imagined. The moment Niels Bohr proposed his model of the atom, reality quietly shifted. Before Bohr, atoms were imagined as miniature mechanical systems, tiny solar systems where electrons orbited the nucleus in smooth, predictable paths. This picture felt reasonable because it mirrored the visible universe. Planets move around stars, so why shouldn't electrons move around nuclei? Yet this comforting analogy carried a fatal flaw. According to classical physics, an orbiting electron should constantly lose energy. Overthinking brings punishment and collapse into the nucleus. Atoms, and therefore matter itself, should be unstable. The fact that the world exists at all was a direct contradiction of classical logic. Bohr's insight was not to fix the classical picture, but to abandon it. He proposed that electrons are allowed to occupy only certain discrete energy states. In these states, they do not radiate energy, even though classical physics insists they should. This idea was shocking because it introduced rules that had no mechanical explanation. Electrons simply were allowed to exist in certain ways and forbidden from existing in others. Nature, according to Bohr, was not governed purely by continuous motion, but by quantized possibilities. This shift was essential for understanding magnetism. If electrons behaved classically, magnetic effects would be wildly unstable and unpredictable. The simple fact that magnets exist in stable forms already hinted that atomic behavior must be constrained by deeper rules. Bohr's atomic model provided the first clear framework for those constraints. Within Bohr's view, electrons are described not just by where they are, but by how much energy they possess. These energy levels define the structure of atoms and determine how electrons interact with one another. Magnetism emerges from this structure. It is not added on later as a separate force. It is built into the quantum architecture of matter. One of the most revolutionary implications of Bohr's model is that electrons do not have well-defined paths. Instead, they occupy regions of probability. This means that the classical idea of an electron as a tiny circulating charge generating a magnetic field becomes meaningless. You cannot draw a simple loop and say, "This motion causes magnetism." The cause is no longer mechanical motion, but quantum state. As quantum theory developed, Bohr's ideas merged with new discoveries, especially the realization that electrons possess spin. Spin fits naturally into the quantum framework Bohr helped create. It is quantized, intrinsic, and governed by strict rules. Each electron carries a magnetic moment because of its spin, and the way these spins are arranged depends directly on the allowed quantum states of the atom. Bohr emphasized that atomic structure determines physical properties. This principle is crucial for magnetism. In atoms with filled electron shells, spins pair up and cancel. These atoms contribute almost nothing to magnetism. In atoms with partially filled shells, unpaired spins remain. These unpaired spins are the seeds of magnetic behavior. Whether those seeds grow into observable magnetism depends on how atoms interact in solids. The quantum structure of solids is an extension of Bohr's atomic vision. When atoms come together to form a solid, their electrons do not remain completely isolated. Their quantum states overlap, interact, and reorganize. This reorganization determines whether electron spins align or oppose one another. Magnetism is therefore not an isolated atomic property, but a collective quantum phenomenon shaped by atomic structure. What makes this so unsettling is how little room there is for classical explanation. In a magnetic material, electrons align their spins across vast numbers of atoms. This alignment can persist even when the atoms themselves are vibrating due to heat. Classical physics would predict chaos. Quantum mechanics predicts order, as long as certain energy conditions are met. Bohr introduced the idea of complementarity, the notion that quantum objects cannot be fully described using a single classical picture. This idea applies directly to magnetism. A magnet can be described as producing a magnetic field, which is a useful classical concept. But the origin of that field cannot be understood without abandoning classical imagery. The magnet is both a solid object and a quantum system. These descriptions are not contradictory, they are complementary. This duality explains why magnetism feels so familiar and yet remains so deeply strange. On the surface, magnets obey simple rules. Like poles repel, unlike poles attract. Beneath that simplicity lies a quantum reality where electrons occupy abstract states, constrained by rules that defy visualization. The classical behavior is an emergent summary, not a fundamental explanation. Another key contribution of Bohr's thinking is the idea that observation and description matter. In quantum mechanics, how a system is described determines what can be said about it. Magnetism is often treated as a field permeating space, but this field is a macroscopic description of countless quantum interactions. The field is real in its effects, but it is not a fundamental object in the classical sense. The stability of magnetic materials is one of the strongest pieces of evidence for Bohr's quantum framework. A magnet can sit on a refrigerator for years without losing its strength. This stability arises because the electrons are locked into a quantum configuration that is energetically favorable. Transitions to non-magnetic states require energy that is not readily available at ordinary temperatures. This also explains why magnetism can suddenly vanish when conditions change. Heating a magnet supplies enough energy to disrupt the quantum ordering of spins. Once the electrons can access different quantum states, the collective alignment breaks down. The magnet does not gradually weaken in a classical sense. It undergoes a quantum phase transition. Bohr's atomic model also helps explain why magnetism is selective. Only certain materials can become strong magnets. This selectivity is not accidental. It is dictated by electron shell structure and quantum energy levels. Elements with the wrong electronic configuration simply cannot support the necessary spin alignment, no matter how they are treated. This realization challenges the intuitive idea that magnetism is a universal property waiting to be activated. Instead, it is a rare outcome of specific quantum arrangements. Nature allows magnetism only when atomic structure permits it. This makes magnets less like fundamental objects and more like special solutions to quantum equations. Perhaps the most reality-shattering implication of Bohr's answer is that magnetism does not originate in space between objects, but inside matter itself. The magnetic field extends outward, but its source is the quantum state of electrons within the material. Space does not pull iron toward a magnet. Quantum, structured matter shapes space in a way that produces magnetic effects. In this sense, a magnet is not merely an object exerting a force. It is a frozen pattern of quantum information. Its strength, direction, and stability are encoded in electron configurations that cannot be seen or imagined in classical terms. The magnet works because those configurations are allowed, and alternative configurations are forbidden. Bohr believed that quantum theory forces us to rethink what it means to explain something. Explanation no longer means building a mechanical model. It means identifying the rules that constrain behavior. Magnetism fits this perfectly. We do not explain a magnet by showing tiny gears or currents. We explain it by showing which quantum states exist and why they persist. This perspective transforms magnetism from a curiosity into a philosophical statement about reality. It tells us that the physical world is not constructed from intuitive building blocks. It is constructed from principles that only reveal themselves through mathematics and abstraction. The fact that these principles produce something as tangible as a magnet is both astonishing and humbling. When you feel the pull of a magnet, you are not feeling a simple force. You are feeling the outcome of Bohr's quantum revolution. You are feeling the consequence of electrons obeying rules that have no classical meaning, yet govern the structure of everything around you. Magnetism, seen through this lens, is not just a property of matter. It is proof that the universe runs on quantum logic, even when it appears solid and familiar. One of the most unsettling realizations in modern physics is that magnetism, something that feels so solid and dependable, is governed by rules that are anything but intuitive. At the center of this realization is the role of electron spin and the strict quantum laws that dictate how electrons are allowed to exist. Unlike classical properties such as position or speed, spin is not something electrons acquire through motion or interaction. It is an intrinsic feature, present even when an electron is completely isolated. This single fact overturns the traditional idea that magnetism must arise from movement or mechanical processes. Electron spin introduces a new kind of order into nature. Each electron carries a tiny magnetic moment, behaving like a minuscule magnet with a direction in space. But unlike classical magnets, these quantum magnets do not point freely in any direction. Their orientations are quantized. They can only take certain values, dictated by the mathematical structure of quantum mechanics. This restriction is not optional. It is as fundamental as the speed of light or the charge of the electron. The consequences of this quantization are profound. In an atom, electrons arrange themselves in orbitals defined by energy, shape, and orientation. When electrons share the same orbital, quantum rules force their spins to be opposite. This pairing is not caused by repulsion or attraction in the classical sense. It is enforced by the Pauli exclusion principle, a rule so abstract that it has no classical analogy. Yet it is this rule that determines whether matter is magnetic or not. Most atoms in everyday materials have their electrons neatly paired. Each spin-up electron is matched with a spin-down partner, canceling their magnetic effects. The atom, as a whole, produces no net magnetic field. Multiply this by trillions of atoms, and the result is matter that appears completely non-magnetic. Classical physics would struggle to explain such widespread cancellation. Quantum mechanics makes it inevitable. The rare cases where electrons remain unpaired are where magnetism begins. Certain atoms, particularly those with partially filled electron shells, cannot pair all their electrons without violating quantum energy rules. These unpaired electrons carry magnetic moments that do not cancel. On their own, they are weak and insignificant. But when these atoms come together in a solid, a new level of quantum behavior emerges. In a magnetic solid, unpaired electron spins do not act independently. They interact through quantum mechanical forces that favor alignment under specific conditions. This interaction, often called exchange interaction, has no classical counterpart. It is not a force transmitted through space like gravity or electromagnetism. It arises from the requirement that the combined quantum state of electrons be consistent with the exclusion, principle, and energy minimization. The exchange interaction explains why electron spins in a magnetic material tend to align parallel to one another. This alignment lowers the overall energy of the system, even though classical reasoning would predict increased repulsion between like magnetic moments. Once again, intuition fails. Nature does not choose what feels reasonable. It chooses what satisfies quantum rules. When many spins align, their magnetic moments add together. The result is a macroscopic magnetic field. This field extends beyond the material, influencing other objects and interacting with space itself. Yet its origin remains entirely internal. It is the collective expression of quantum constraints acting on electrons. What makes this truly astonishing is how stable this alignment can be. Atoms in a solid are in constant motion, vibrating due to thermal energy. Classical thinking suggests that this motion should randomize spin orientations, destroying magnetic order. Quantum mechanics, however, predicts that as long as the energy required to flip spins is greater than the thermal energy available, the alignment will persist. Stability emerges not from rigidity, but from energy gaps and forbidden transitions. This stability gives rise to the phenomenon of permanent magnets. A permanent magnet is not permanently active in the classical sense. It is trapped in a low energy quantum configuration. The spins are aligned not because they are forced to be, but because alternative arrangements are energetically inaccessible. The magnet remains magnetized because the quantum system has nowhere else to go. The idea that most materials are not magnetic becomes clearer in this context. Magnetism is not the default state of matter. It is an exceptional outcome that requires very specific conditions. The right electron configuration, the right type of atomic bonding, and the right balance of quantum interactions must all be present. If any of these conditions fail, magnetism disappears. This explains why small changes can have dramatic effects. Heating a magnetic material adds energy to the system. Once the thermal energy becomes comparable to the energy that holds spins aligned, the quantum order collapses. The spins become disordered, and the material loses its magnetism. This transition is sharp and sudden, reflecting a fundamental change in the quantum state of the system rather than a gradual weakening. The same quantum sensitivity explains why mechanical stress, impurities, or external magnetic fields can alter magnetic behavior. These influences change the energy landscape of electron spins, opening or closing possible quantum states. Magnetism responds not because it is fragile, but because it is deeply tied to quantum conditions. Perhaps the most unsettling aspect of electron spin is that it has no visualizable origin. We can describe it mathematically with extraordinary precision, but we cannot picture it in everyday terms. There is no spinning object, no axis in space, no hidden machinery. Spin simply exists, and yet, from this abstract property emerges the familiar force that holds a magnet to your refrigerator. This challenges our understanding of explanation itself. In classical physics, to explain something is to show how it works mechanically. In quantum physics, explanation often means accepting that certain properties are fundamental. Electron spin is one of those properties. It cannot be reduced to something simpler. It is a starting point, not a result. Magnetism, therefore, is not caused by motion in the usual sense. It is caused by the existence of electrons with spin and the rules governing how those spins can be arranged. This realization strips magnetism of any comforting mechanical picture. What remains is a logical structure, a set of constraints that shape the behavior of matter. When viewed from this perspective, magnets become deeply philosophical objects. They are tangible evidence that reality is built from abstract principles rather than intuitive mechanisms. They show that something you can hold in your hand can be governed by rules you cannot imagine. The pull between two magnets is not a tug-of war between objects. It is a reconfiguration of quantum fields and spin alignments seeking a lower energy arrangement. The force you feel is the macroscopic signal of microscopic rules being obeyed. Electron spin also reveals why magnetism is directional. Spins have orientations, and alignment matters. The direction of a magnet is not arbitrary. It is defined by the collective orientation of spins locked into a specific quantum pattern. Changing that direction requires overcoming energy barriers set by quantum mechanics. This makes magnetism both robust and delicate. Robust because once established, it can persist for a long time. Delicate because it can vanish when conditions cross a critical threshold. This duality reflects the underlying quantum nature of the phenomenon. In the end, the role of electron spin in magnetism forces us to accept a humbling truth. The world we experience is not governed by the rules we evolved to understand. It is governed by rules that only reveal themselves through careful experiment and abstract reasoning. Magnetism is one of the clearest demonstrations of this truth. It works not because nature is simple, but because nature is profoundly quantum. When magnetism is traced to its deepest origin, it no longer appears as a simple interaction between objects, but as a large-scale pattern emerging from countless microscopic events. This idea, that magnetism is a collective quantum phenomenon rather than a basic force, radically reshapes how reality must be understood. A magnet is not powerful because of any single atom or electron. It is powerful because trillions of quantum entities fall into a shared order, behaving as one system instead of many independent parts. At the atomic level, each electron with an unpaired spin contributes a tiny magnetic moment. On its own, this contribution is unimaginably small. If electrons acted independently, magnetism would never rise above the noise of thermal motion. What changes everything is that quantum mechanics allows electrons to become correlated. Their behavior becomes linked, not through physical contact in the classical sense, but through shared quantum states and energy constraints. This collective behavior is what physicists call order. In a magnetic material, the spins of electrons are not randomly oriented. They form domains, regions where spins are aligned in the same direction. Each domain is a pocket of quantum coherence, a place where countless electrons share a common orientation. The magnet you hold is a mosaic of these domains, some aligned, some opposed, their arrangement determining the magnet's overall strength and direction. The existence of domains is itself a compromise dictated by quantum and energetic considerations. If all spins in a magnet aligned perfectly in one direction, the magnetic field produced would extend far into space, costing energy. By breaking into domains, the system lowers its total energy. This is not a conscious decision, but the inevitable result of quantum systems seeking stable configurations. Even the structure of a magnet reflects the balance of abstract energy terms rather than mechanical necessity. What makes this phenomenon especially striking is that the order extends far beyond the scale of individual atoms. Quantum effects are often imagined as fragile, disappearing at large scales. Magnetism proves otherwise. Here, quantum rules do not merely survive at macroscopic scales, they dominate. A magnet is quantum mechanics made durable. This durability comes from the way energy landscapes are shaped in magnetic materials. The aligned state of spins is separated from disordered states by energy barriers. As long as the system lacks enough energy to cross these barriers, the order remains intact. This is why magnets can retain their properties for long periods without any external input. They are not being actively maintained. They are resting in a stable quantum valley. The idea of collective order also explains why magnetism can abruptly change. When a magnet is heated, the added thermal energy gives electrons access to new quantum states. Once the energy barrier is overcome, spins lose their coordinated alignment. The transition from ordered to disordered is not a smooth fade but a qualitative shift. This is why magnetism disappears suddenly at a specific temperature rather than gradually weakening from the beginning. Such behavior reveals that magnetism is a phase of matter, much like solid or liquid states. It is defined by symmetry and order, not by individual particles. Below a certain temperature, the system exhibits long-range magnetic order. Above it, that order is lost. The magnet has not been damaged, it has simply changed phase. This perspective forces a re-evaluation of what it means for something to be real. The magnetic field that extends into space is real in its effects, yet it is not a fundamental object in the same way electrons are. It is an emergent feature, a macroscopic summary of microscopic quantum order. The field exists because the underlying system is ordered, not because space itself contains magnetic substance. Collective quantum order also explains why magnets interact the way they do. When two magnets approach each other, their domains reconfigure. Spins shift, domains grow or shrink, and the overall energy of the combined system changes. Attraction and repulsion are not primitive forces acting at a distance. They are consequences of systems rearranging themselves to reach lower, energy collective states. This makes the familiar behavior of magnets profoundly non-intuitive. When two magnets snap together, nothing is pulling them in the everyday sense. Instead, the quantum states of their electrons are reorganizing across both objects. The force you feel is the macroscopic response to this reorganization. The idea that order emerges from cooperation also explains why magnetism is sensitive to imperfections. Defects in a crystal, impurities, or mechanical stress can disrupt spin alignment. These disruptions act as obstacles in the energy landscape, pinning domains in place or preventing them from growing. This is why real magnets are never perfect, and why their properties depend so strongly on material history and treatment. Yet, despite this sensitivity, magnetism remains remarkably robust. Even with imperfections, large regions of order can persist. This balance between fragility and strength is a hallmark of emergent phenomena. The system does not rely on perfection at the smallest scale. It relies on statistical dominance at the largest scale. The collective nature of magnetism also blurs the boundary between matter and space. A magnet shapes the space around it, influencing other objects without physical contact. This influence is not imposed externally. It arises naturally from the internal organization of the material. Matter, through quantum order, structures the surrounding environment. This idea resonates far beyond magnetism. It reflects a broader truth about the universe. Many of the forces and patterns we observe are not fundamental, but emergent. They arise when large numbers of components obey simple rules together. Magnetism is one of the clearest and most tangible examples of this principle. From this viewpoint, a magnet is less like a tool and more like a state of matter frozen in time. Its north and south poles are not intrinsic ends, but expressions of how domains are arranged. Break a magnet in half, and you do not isolate a north or south pole. You create two smaller systems, each reorganizing into its own pattern of order. The magnet reasserts its quantum structure at every scale. This behavior is impossible to explain classically. Classical objects can be divided into independent pieces. Quantum-ordered systems cannot. Their defining property is not localized in one part, but distributed across the whole. Magnetism belongs to the system, not to its fragments. The realization that magnetism is emergent also reshapes how technology is understood. Electric motors, generators, data storage devices, and medical imaging tools all rely on controlling collective quantum order. Engineers manipulate materials not by moving charges individually, but by shaping conditions that favor certain ordered states. Modern technology quietly depends on principles that were once considered abstract and philosophical. At a deeper level, collective quantum order challenges human intuition about causality. In magnetism, cause and effect are not always localized. A change in one region can influence behavior far away through the shared order of the system. This interconnectedness is not mystical. It is a direct consequence of quantum rules applied at scale. Perhaps the most reality-shattering aspect of this picture is that the everyday world is not as classical as it appears. Objects feel solid, forces feel direct, and interactions feel mechanical. Yet magnetism reveals that beneath this surface lies a realm where abstract order governs tangible effects. The magnet on your refrigerator is not an exception. It is a window. In the end, magnetism teaches that reality is layered. At one level, there are forces and objects. At a deeper level, there are patterns and rules. And beneath that, there are quantum principles that allow those patterns to exist at all. A magnet works not because nature is simple, but because nature is capable of organizing itself in astonishing ways